When polygons hide their mystery, triangles unlock their history. Each split a choice, each score a fate. We seek the minimum before it's too late. Welcome everyone. Today we embark on a mathematical journey into the world of polygons, where hidden among vertices and edge lines a fascinating problem, the minimum score triangulation of a polygon. We are given a convex polygon with n vertices, each vertex holding an integer value. Our task is to divide this polygon into triangles only. Every triangle has a weight, which is the product of the three vertex values that define it. The overall score is the sum of all these triangle weights, and our ultimate goal is to find the minimum possible score across all valid triangulations. Consider the simplest case, a triangle itself. With input values 1, 2, and 3, the polygon is already triangulated. The score is simply the product 1 into 2 into 3 equals to 6. Thus the answer is 6, straightforward, but it builds the foundation. Now take values 3, 7, 4, 5. Here there are multiple triangulation choices. If we choose triangles 3, 7, 5 and 7, 4, 5, the total is 245. If instead we choose 3, 4, 5 and 3, 4, 7, the total becomes 144. Among these, 144 is the minimum, which is our desired answer. For 1, 3, 1, 4, 1 and 5, many triangulations are possible. Some choices give large values, but after calculating all possibilities, the smallest achievable score is 13. This shows how critical it is to carefully choose the order of splitting. Let's pause for a moment. A polygon with n vertices will always split into exactly n-2 triangles, but the order in which we cut directly affects the total score. Brute force would mean checking every possible division, which quickly becomes impractical as n grows. This observation pushes us towards a smarter solution, dynamic programming. To solve this efficiently, we define a state, dpij equals to the minimum score required to triangulate the polygon from vertex I to vertex j. If there are fewer than 3 vertices between I and j, no triangle can be formed and the score is 0. How do we build this? For every pair of vertices I and j, we try inserting a third vertex k between them. This forms a triangle ijk and leaves us with two smaller subproblems, triangulating ik and kj. So the formula becomes dpij equals to minimum over k dpik plus dpkj plus values I times values j times values k. This recurrence captures the essence of the problem. The solution requires three nested loops, one for the length of the intervals, one for the starting points, and one for choosing the middle point. Thus the time complexity is big of n cube. The space complexity is big of n square since we store results in a 2D table. Fortunately, with n less than equals to 50, this is very efficient. We build solutions step by step. First, consider short intervals, then gradually move to longer intervals. For each interval ij, we compute dpij using all possible choices of k. This ensures that when we compute a larger interval, all its smaller subproblems are already solved. Here is the complete C++ implementation. It follows the exact idea we discussed. Initialize dp with 0, expand intervals of increasing length, and compute the minimum scores using our recurrence. Finally, the result is stored in dp0 n-1. Let's revisit the example 3, 7, 4, 5. First, compute smaller subproblems like 0, 1, 2 and 1, 2, 3. Then build up the full interval 0, 3. Trying both options 0, 1, 3 and 0, 2, 3 leads us to scores 245 and 144. And of course, we choose the minimum 144. There are two ways to implement this DP, top-down or memoization. Recursive, easier to think about, bottom-up or tabulization. Iterative avoids recursion depth and is slightly faster. Both approaches achieve the same big of n cube complexity. Think of the polygon as a cake. Every time you cut it into triangles, you incur a cost. Some cutting orders waste ingredients, others save them. Dynamic programming ensures that we discover the cheapest way to slice the cake. In summary, we solved the minimum score triangulation problem using interval dynamic programming. We defined a clear state dpij, applied a recurrence relation, and computed the results step by step. With big of n cube time and big of n square space, the algorithm is efficient for the given constraints. This problem is beautifully demonstrating the power of optimal substructure and how DP transforms an exponential brute force into a practical solution. Thank you for your attention.